Okay, so we're done with the regularity lemma. So we're on the 6th chapter, the notes. To be honest, this chapter is mainly an assortment of things that I just think are kind of cool and interesting. But they are sort of tied together by the topic of independent sets. What's an independent set in a graph? It's probably a lot of you know, but so a set S in the vertex set of a graph, so G is a graph, is independent if there does not exist UV in S such that UV is an edge of G. Okay. Some people call them stable sets. There's various different things, but I think the most common thing to say is independent set. Another definition, the biggest independent set in a graph is denoted by alpha of G. So alpha of G is the max cardinality of S such that S is an independent set in G. Okay. So the question we're going to be addressing today is, suppose you have a graph that's triangle free. How big of an independent set can you guarantee? Question. So what is kind of the minimum possible alpha of G in a graph with n vertices and no triangle, so no K3. So, I mean, we've looked at problems involving triangles a lot. For example, Mantle's theorem was like, I want to have no triangles and have as many edges as possible, right? Which in principle sounds kind of related because, having a lot of edges would kind of suggest you don't have, edges are the best thing for breaking independent sets, right? But if I take the construction from Mantle's theorem, it has really big independent sets, right? N over 2. That's not going to be the best you can do. So this is kind of a different type of question. So we want to minimize alpha of G in a graph with n vertices and no triangles. We're not going to be able to exactly answer this question because it's kind of still an unsolved problem. But we're going to get like basically the best bound that anyone knows how to prove. So this is a result of Shearer. So let f be the function from the non-negative real, so 0 to infinity to the reals, be defined by, so f of x, it's going to be a piecewise definition. So it's 1 if x equals 0, it's equal to a half if x is 1, and otherwise it's x ln x minus x plus 1 over x minus 1 squared. Okay. Kind of a technical function. I mean, might not be clear how the heck could we prove anything about this, but this turns out to be exactly the right thing. So the statement of the theorem is if G is a graph with no triangles and with n vertices, then alpha of G is at least f of 2 times the number of edges of G over n times n. Okay. So this is actually, this bound is somewhat more detailed than what I'm, in this question I was just describing, like, you have a graph on n vertices and you want to minimize the independence number. This is actually sensitive to not only the number of vertices, but also the number of edges. This will give you a bound. If you input some number of vertices, some number of edges, it'll give you some kind of bound, right? And if I wanted to get a bound that works for all graphs on n vertices, I would just minimize f over all choices of the number of edges, like given n vertices, right? So this will imply a bound that hold, for any n. But in fact, it's more kind of detailed than that, right? It depends on the number of edges. Is the statement okay? I mean, it should not be clear at all how this is going to come into play, but we'll see. Essentially, maybe I'll spoil it and say, at some point, we're going to go through some calculation where actually the function f will not matter for most of the proof. And then at the end, we're going to say, we want a certain differential equation to be satisfied, and this will be the solution to it. And then we'll just say, yeah, then it works. So in some sense, you don't get like too hung up on what this is, and we'll just see at the end, this is the right for that differential equation. It maybe is worth just, or maybe I'll do it on this board, just kind of seeing what this function kind of looks like. So at 0, this function is equal to 1. At 1, it's equal to a half, right? The reason we had to do it piecewise is because of issues like dividing by 0, right? If I plug in 1 into this function, it would be dividing by 0. If I plug in 0, ln of 0 is not defined, so that's kind of an issue as well. But it turns out, like, this piecewise definition, I mean, essentially, this function is kind of continuous, and it's not such a bad function. And we're just kind of putting in, the piecewise thing is just putting in these points where it wouldn't be defined otherwise. So it's some kind of a function that's kind of curved like this. This might not, I don't know, the way I've drawn this kind of sucks. It looks like it's not going to any kind of asymptote or anything like that. It decays down to 0 basically, right? But one thing you can check is that the second derivative of this function, if you really wanted to compute it, it's always going to be non-negative, which just means which implies that this function's convex. And this is going to be important. So f is convex. And really what we're going to use this for is to say that if I take the tangent line at any point, the tangent line to this curve always lies below the curve. So the tangent line at, say, x equals x naught lies below f for all points x naught. Okay. So, okay, we're going to use two things about this function. We're going to use, eventually we'll use that this is the solution to some differential equation, but also we're going to use that it's convex. And the way we're going to use that is just in terms of this tangent line condition, right? And it's kind of clear that, right, if I, the tangent line is going to lie below the curve. And that's something that happens for convex functions. For example, for x squared, right, if I take the tangent line, it always lies below the thing, right? Okay. So let's try to prove this theorem. The proof of this theorem is actually kind of nice. Here's the idea. Let's do this, one of the simplest possible algorithms I could ever imagine for finding an independent set. And let's just analyze it. So here's a very simple independent set algorithm. Pick a random vertex. Okay. And when I say random, I mean every vertex is equally likely. So every vertex has probability 1 over n. Put it in the independent set. Okay. But if I'm going to basically repeat this over and over and over. But if I do that, I have to be careful because now that I've picked a certain vertex, I cannot pick any of its neighbors, right? Because that would be illegal. That would not make it an independent set. So third step, delete that vertex, so the vertex and its neighbors. And then just repeat. As long as there's some vertex still left to choose, so. Okay. So yeah, it's not a terribly difficult algorithm, right? I mean, I kind of can't think of anything more simple in some sense. Maybe the randomness is, you could think of that as clever, but it's not really that clever, right? I mean, yeah, just pick a random vertex, put it in the independent set. Okay, so, well, maybe something I should have said at the beginning. This proof is going to go by induction on n. So we proceed by induction. So basically, we are going to analyze this algorithm. The case n equals 1. Well, when n equals 1, the number of edges has to be 0. And the bound we're trying to prove is just alpha of g is at most, or is at least 1, but that's just true because just take the vertex in the graph. So that's easy. Because 1 will be f of 0 times n, times 1 or whatever, right? Okay. Okay, so for each vertex, V, let GV be the graph obtained from G by deleting V and its neighbors. So I guess the reason for this definition, right, it kind of relates to this algorithm. So essentially what we're going to do, so alpha of g is at least what I would get from this algorithm, which is like, 1 over n. 1 over n is to account for, so think of each vertex gets chosen with probability 1 over n. I'm going to sum over all the vertices. And then I'll say, well, the size of my independent set is, so I'm going to assume, like, sum over all the vertices and assume V is the one that's chosen. So I would have one thing in my independent set for V. I would then delete V and its neighbors. And whatever lower bound on the independence number I would get from this algorithm on GV is what I would get the number of additional vertices I would get. So actually, really, maybe you should think of this as being, what I'm writing here is true, but I guess we're going to think of this as, this is what the algorithm would give you in GV. Is that clear? So this is kind of summing over choices for the first vertex of the algorithm. When I choose that vertex, I put it in the independent set, which turns my independent set from 0 to 1, and then I take the biggest independent set I could in the rest of the graph. But I have to leave V and its neighbors, right? Okay. And the good thing about this is we can apply induction, right? GV is smaller, so we can apply induction on it. Okay, so let's introduce a bit of notation. So let's let D be 2 times the number of edges over n. So the reason I'm using D is because this is the average degree, right? Because if you sum the degrees, it equals 2 times the number of edges by handshaking. So this is the average degree. So if I just kind of say, what do I want in the end? We want alpha of g to be at least f of d times n, okay? Because that's what this is just d, right? Okay. So by induction, well, Okay, so sorry, let's also define another thing. I'll define d sub v to be the same quantity but in GV. So it's 2 times number of edges of GV over n minus the degree of v minus 1, because this is how many vertices G of v has, right? Kind of realizing maybe there's an issue here of dividing by 0 or something in the case where maybe every vertex is adjacent to v or something. Let's not worry too much about that. This is one specific graph, and we could show that it satisfies the inequality anyway. So, so yeah, let's not worry too much. This could actually be dividing by 0, but let's assume it isn't, because yeah. So what we have on the other board, so we know that alpha of g, so I'm just rewriting what we have on the other board. And then by induction, we can assume this is at least 1 over n, sum over all the vertices in G, 1 plus so f of dv times the number of vertices of GV, which is n minus dv minus 1. So this is by induction. Do we agree with that? So yeah, this is just copying what we had on the other board, and this is just replacing that with the lower bound we would get by applying the theorem to GV. Okay. But here's the thing, like, this by itself is pretty hard to analyze, because like different vertices will have a different value of dv. They're going to have a different, this is going to change, you know, for different vertices. This is going to change. And like then I have to apply f to it, and f is like this complicated function. I mean, and at the end of the day, I want a bound involving f of d, and like this is just not that. But using the convexity of the function, what we're going to do is essentially try to replace this with something involving an f of d. So, right. Well, so let's forget about the actual values. So we've got something in terms of f of dv, a lower bound. Like suppose f of d is here, and suppose d is here, and you know, dv is here for some vertex v. If I take if I just go through the tangent line here, and I just take the kind of value of the tangent line at that point, it's going to be less than or equal to f of dv, right? So if I kind of think about what that would correspond to, it's not, so for any vertex v, the value of f of dv is at least the value I have for the tangent line. Like if I take the tangent line at x equals d and I run it to x equals dv, it's at least that. So so this would be like f of d plus f prime of d times dv minus d. I'm about 60% sure I've got that right. Does that seem right to you guys? I take, how do I get the tangent line? I take, so when d is equal to d, like the tangent line should be, it should be equal to f of d and then follow the slope for that distance or something, right? Yeah. So I think that's correct. So now if I plug this lower bound, in here, so the independence number is at least 1 over n, sum over all the vertices, 1 plus, so I'm going to put in f of d plus f prime of d dv minus d, and minus d of v minus 1. Okay. Okay, so I'm just replacing this thing with this thing, and it gets smaller. Okay. Maybe you can start seeing that at this point, maybe there's going to be some kind of differential equation that shows up because I've got the f with the derivative of f. Somehow that's going to, yeah, something's going to happen like that. Okay, let's reorganize this a bit. Okay. This is going to be a bunch of algebra. Just going to multiply in my f prime of d. Apologize that that's kind of cramped, but all I did was multiply that in, distribute. Right. So all of these ones, like every single term has a 1, and then I divide it by 1 over n, or I divide it by n. So this 1 can kind of like be taken out because it's like there's n of them, and then I divide by n. So this is the same as 1 plus well, let's do two things at once. I'll pull out that 1, like I said, and then I'm going to kind of separate this part times this from the other ones. So this is 1 over n f of d minus f prime of d times d, n minus the degree of v minus 1. And then I'm going to separate off the other thing, which was like a 1 over n sum over, so all of these sums are over all the vertices. F prime of D times D sub V times n minus degree of V minus 1. Okay. Shouldn't necessarily be clear where this is going. But here's one nice thing about this. If we remember how did I define my dv? So it's 2 times the number of edges of gv, right, over n minus dv minus 1. If I was to plug that back in, it's going to, the n minus degree of v minus 1 is going to cancel, right? So that's one nice thing. So maybe let's do that. Maybe let's also, well, what's going to happen here? Oh, yeah, so let's do a couple of things. So I've got 1, again, 1 over n. The thing is, none of this depends on v. Like, this is summing over all the vertices, right? I guess that's why I've separated it this way. This is like the stuff that depends on the vertex v. This doesn't. Of course, this does. But I'm saying this coefficient doesn't. So that could be pulled out, right? And then when I sum this over all the vertices, well, this n just becomes like an n squared. Summing over all the vertices of the degree, well, that just gives me 2 times the number of edges, which is the same as d times n, right? Because d is 2 times the number of edges over n, which is the sum of the degrees over n. Summing, yeah, so the sum of the degrees is d times n. And then minus n. Okay. Then I've got this term. The f prime of d doesn't depend on n. Okay. Like I said, dv is 2 times the number of edges in gv over exactly this number. So this is just like 2 times the number of edges in gv. Okay. With me so far? A lot of algebra and stuff. Okay. Maybe I want to analyze this. When I delete a vertex, I delete the vertex v. I guess the question is, how many edges do I lose? Sorry, I delete the vertex v and its neighbors, right? So let's say so define, say, d2 of v. So I know there's a lot of things like that are d of v or with subscripts and things like that, but d2 of v, let's say that this is the sum over all the neighbors of v of the degree of that neighbor. So then if I want to know how many edges does g of v have, I claim that it's equal to all the edges we had before, which was n times d, because of how d is defined. Or, sorry, maybe I'll say 2 times this is n times d, and then minus d2 of v, although, something seems a bit off by a factor of 2 or something. I think this must be, sorry. Well, okay. I think it must be like this, but we'll see what happens. So here's the point. This is actually where we're using triangle freeness, believe it or not. So imagine you've got a vertex V. I delete V and its neighbors, and I want to know how many edges do I lose. Well, the thing is, V is not in any triangles, right? So like, what does it look like when I look at the kind of like none of its neighbors are adjacent, right? So when I right, so when I delete V and its neighbors, I'll lose one edge for the degree of this vertex, that many edges, like 4 edges for that vertex, 3 for this one, because I'm counting the one that goes to V as well, right? I'll lose, and because there's no triangles, I'm not double counting any edges I've deleted, right? This is going to be exactly how many edges I lost. Does that make sense? Okay. So I think this should be correct. Okay. So now let's put that in. Okay, so just kind of, right, what we're doing, we're still lower bounding alpha of g. So I'm just going to kind of rewrite this expression and simplify it a bit using this. So it's like 1 plus, so the 1 over n, there's a bunch of n's that can cancel. So it's like f of d minus f prime of d times d times n minus d minus 1. So I've just canceled the 1 over n with the n inside the second factor there. Plus 1 over n f prime of d sum over all the vertices of n times d minus d2 of v over 2. Nope, times 2. Okay. So here's the kind of key observation. If you think about what this is pick a vertex, pick a neighbor of that vertex. Right? This is like pick a vertex V, and then I sum over all the neighbors of V, and I take their degree. So it's kind of like picking a vertex, picking a neighbor, and then picking another neighbor, which we've seen it a million times. This is counting walks of length 2 in the graph. And we also know if you count that another way, it's like, you know, I could count it by starting with the middle vertex and taking 2 neighbors of it. So this is just like, this counts walks of length 2. I almost feel like at this point, this course should just be called like applications of sums of like this inequality all the time, right? So this is like a lower bound on the sum of the kind of D2 thing, which like that's in here somewhere. It may seem like this is going the wrong way though, right? Because I've got a negative coefficient on that here. Like I want to get a lower bound on this whole expression, right? This is getting a lower bound on this D2 of thing, and I've got a negative expression or negative coefficient there, which kind of looks bad, right? But can anyone see why it's not bad? Yeah, you got it. Yeah, the derivative of f is negative, right? So it's like it's actually a positive coefficient because a negative. This is a negative, so it's actually a positive coefficient on this thing. So I can lower bound it in that way. And this, by the way, is the same as 1 over n d squared. So it's like n times d squared. Okay. So since like my f prime of d is negative, or let's just say non-positive, but it's really negative, we can lower bound this by, okay, same thing as before. For the first few terms, and then plus, so I'm going to bring in this 1 over n and cancel stuff. Let's do that. And I'm going to sum over all vertices. So this first term would give me n squared d when I sum over all the vertices, and one of the n's cancels. This thing would give me what I've got here, 2 times, but with a 2. So 2 times n d squared, and then I cancel one of the n's, or the n because of this 1 over n. And there's still an f prime of d. I apologize, the algebra of this is really annoying. The principle, the idea is kind of nice though, right? We just do like the simplest possible algorithm for finding an independent set, pick a random vertex, delete it and its neighbors, and keep going. And somehow it gives you a nice result. But the analysis is kind of ugly. Okay. Let's get all the things with an n together. And here's a nice thing. Most of them cancel. Because look, I've got an f prime of d, d, n. I've got the same thing. F prime, d, n. They cancel. I've got an f of d, n. And that's like the thing that I want, right? At the end is my lower bound. So this is like f of d times n. And that is the only term with an n. The rest is just stuff with d's and f of d's and stuff. So, so minus, say, like d plus 1 f of d plus d plus 1 f prime of d times d minus 2 times f prime of d times d squared. In some sense, I don't really care what any of this stuff is except for this one. Because now I'll just say, I mean, we're not going to check this, but f is just chosen so that for all x, this is 0. So if you, like, this is setting, oh, sorry, and there's a plus 1 as well. Anyway. So if f is the function that satisfies the differential equation, like where all of this stuff is 0, like set this thing equal to 0, if you take the derivatives and stuff, and if it works out, if it is the solution to that differential equation, then this part is 0, right? And so, can check that f satisfies, because all this stuff has no n's in it, it's just d's, right? That this stuff is, is 0. So we get the bound that we wanted, f of d times n. Okay, so in some sense, we didn't really care that much about what f was, except we wanted it to be convex so we could do this tangent line thing. And then you just say, oh, just make it the solution to this differential equation. And then, of course, you have to hope that it is convex when you do that, but it turns out it is. Okay. Any questions about that? If you wanted to get actually so the initial question I asked was to find a bound in terms of n, but if you sort of optimize your choice of d, what it gives you as a corollary, so I won't go through this, but is that, so if g is, triangle free and has n vertices, then the independence number is at least 1, let's say, well, 1 plus the low 1 root of n times the natural log of n over 2. And it's also known, so this is beyond the scope of this course, but it's known that there exists triangle-free graphs with independence number big O of root n log n. So really, this is pretty much as good as you can do up to a constant factor.